So welcome everybody. Welcome to the Computer Science Department. We are honored to have Professor Donald Knuth giving the Kanellakis lecture this year. Paris Kanellakis was a distinguished member of our department that unfortunately died in a plane accident together with his family, and we're honoring every year with a distinguished lecture his memory. I'm going just to say 2 words about the organization of this event. So we have Professor Eli Upfold introducing Professor Knuth. After the distinguished lecture, we will have a break, and we'll go and start the reception, which is going to be part of this celebration. At the reception, we're going to have a toast honoring 50 years of seminal discussion between Professor Knuth and our colleague Peter Wegner. After this toast, we are going to come back here, and it's going to be a panel discussion in which graduate students and all of us will ask tough questions for Professor Knuth. It's called All Questions Answer Panel Session. So a lot going on. So I'm going to ask Professor Eli Upfold to introduce our speaker.
Thanks. So before saying anything, I have to say I should say that this is the largest audience we ever seen on this floor. That's beautiful. In the Kanellakis annual talks here, we had many distinguished speakers, but there are very few people who had such a profound and long-lasting impact on the development of computer science as our guest today. And so it's a great honor to introduce Professor Knuth, who officially is the Professor Emeritus of the Art of Computer Programming at Stanford University. Yeah, that's what you see there. And I will not list all his awards because then there would be no time for the talk. But I just want to quote, or first say that for the young people here, our guest got his Turing Award in 1974. Yeah, that's before many of us knew about computer or computer science or even existed, the young people around here. And the award was for his major contribution to the analysis of algorithms and the design of programming languages, and in particular for his contribution to the art of computer programming. So his well-known books in continuous series by this title. Well, this was a very modest quote, because it's not really true that Professor Knuth contributes to the analysis of algorithms. In large extent, he started the analysis of algorithm. So an area that so many of us are working in was actually started by our guest. And of course, you know, the books are still coming along. We're still waiting for the next one, and it is really covering all of computer science, and it's beautiful. I just mentioned that our guest also has received the National Medal of Science, and that was from President Carter, the Kyoto Award, you know, and almost any other prize possible, and many more. But here in Brown, I just should say that Professor Knuth is also received honorary award, honorary PhD here in '88. Some of you have been here. I was not here. And last and most important, his daughter went to Brown. So he's also a parent, okay? And so, needless to say that he's also a member of all the possible academies and another few, okay? And so it's a great pleasure to introduce Professor Knuth, who's going to talk about Hamiltonian paths in antiquity.
Okay, well, of course, it's an honor for me to be here, and it's also a treat to see so many friends that I haven't seen for a long time. Now, this is going to be show and tell, and I'm going to learn how to use this machine that projects here. So in other words, by zooming, I should be able to zoom in and zoom out and things like that. So we'll see what happens. But I brought a lot of stuff that I want to show you and tell you about. And actually, what I'm going to today, I'm going to tell you a story that I don't think has ever been told before, and it's just waiting to really be told properly because I've only done the initial investigation into it. So as I'm writing my books, of course, one of the important topics that I want to discuss as part of our computer programming is the whole idea of Hamiltonian paths, and one of the things I try hardest to do in my books is to try to get the history right. And so I've been learning over the years more and more things about Hamiltonian paths, and especially last year and this year, some things that I think you'll find as surprising as I did. And well, I couldn't wait for the historians to tell the story because they don't get Hamiltonian paths. So here I'm going to sort of tell you what I know about it so far, and presumably there's a lot more will remain to be told later. So okay, now but I can also. Since I got so many people in this room, I can also maybe recruit a few people to proofread my book. So you know, I try to get the story right, but there's on every page there's several hundred things I could get wrong. So even when I was when I was a student, I didn't get 100% on every exam. So let's suppose that I want to get 99%. Okay, that means I have 3 errors on every page, right? If there's 300 ways I could. Anyway, if you find an error, you send me an email to this special address for reporting bugs. And then, in due time, I look at it, and if it was indeed an error, and nobody else reported it first, then you win $2.56, and that also goes for these prefascicle. Now, you see what this says, prefascicle here? That means that it's not even out in paperback yet. This is before beta testing actually, and I wake up in the morning and I think of something that's going to go in something I haven't written yet. I'll maybe put it in one of these prefascicles. And so this particular thing is out there on the web, but there's no link to it. But there is a link to prefascicle 5A. So if you look at that link and you use a little thought, you might be able to figure out how to download prefascicle 8A. And I have to tell you that at 1:30 this afternoon, I found an error in prefascicle 8A. So if you had done that yesterday and read this, you would have, you would have actually earned $2.56. So how's that for you? Now there are 4 other hidden ones that there aren't links to, and there's one I think only one person in the world has discovered so far, but a good hacker would be able to find all of the ones that are out there, in nebulous form. But so as I learned this story that I'm going to tell you about today, I started putting it into this section, which is going to go in eventually in a paperback called Fascicle 8, and fascicles 0 through 4 of volume 4 were in paperback, but then they eventually came out in hardcover, and fascicle 6 is already out in paperback. That's going to be the middle third of volume 4B, and fascicle 5, there's 5A, 5B, and 5C as prefascicles I'm currently working on them, but probably that'll be published maybe next summer. And so on, but slowly but surely, I'm trying to get the story in here. Now, so what is Hamiltonian cycles? It starts out, of course, with Mr. Hamilton, who's named after, and well, I got a quote, but you don't have to read this particularly, but the thing is, he got named after him because he popularized it, because he made up this game that they called the Icosian game. So let me show you the Icosian game. I think I'm gonna move to the side so that I can look at the screen when I do this and get. Okay, so the Icosian game, there are two great collections of puzzles in the world. One is the Puzzle Palace in England, and one is the Jerry Slocum's collection in Indiana, and there are only four copies known now of this game, which Hamilton invented, and he called it the Icosian game because it has to do with icosahedrons. Now, but the funny thing is that if you look at all the Wikipedia references to the Icosian game, it doesn't say anything about icosahedrons at all. Icosahedron is a polyhedron with 20 sides. They say it has to do with a dodecahedron, which is a 12-sided thing. And if you look at this picture here, it looks pretty much like a dodecahedron with the pentagons and actually there's another game that came out a year later called the Traveler's Dodecahedron, which is a similar thing. To add a dodecahedron, and you're supposed to find routes between places on the thing. So why did he call it the Icosian game? My answer is that the icosahedron and the dodecahedron are very closely related to each other. They're duals of each other. So if you talk about the vertices of a dodecahedron, you got 20 of them, and those correspond to the faces of the icosahedron. And if you look at the vertices of the icosahedron, there's 12 of them, and they correspond to the dodecahedron. Okay, so let me show you that picture. You see here's the icosahedron has triangles, 20 triangles. Dodecahedron. So every triangle is surrounded by five. Has five. I'm sorry. The dodecahedron has pentagons and is surrounded by 5 pentagons. Every triangle is, of course, surrounded by 3 other triangles. But the total numbers turn out so that these are dual as graphs. Now, now, what is the problem that Hamilton wanted to do? If you talk about a dodecahedron, it'll say try to go along the vertices of a dodecahedron and hit every vertex exactly once. And that's called a Hamiltonian path now, as most of us know. What does it look like on the icosahedron? Well, it says take every triangle on that icosahedron and make a tour that go from triangle to neighboring triangles and come and hit all 20 triangles without repeating. So that's the Icosian puzzle. It really wasn't much of a game, and Hamilton sold it for 25 pounds to this puzzle maker, and I think that he got a good deal out of it because the puzzle maker evidently didn't sell enough of them to make an impact on the market. Well, anyway, that's the sort of the known history of the game. But I ran across a curious thing a few years ago, and I saw an icosahedron that was actually labeled with Greek letters. And this thing was well, the date isn't exactly known, but it's Greco-Roman times, which means that it's probably something like 200 AD. Sometime, maybe as late as 400 AD or something, but let's say 1800 years ago. And so here was an icosahedron, and it's got, if you look a little bit, you can see, I guess I put my finger here, then you can see, here's an alpha, here's a beta, here's a kappa, theta, epsilon. And so, you can sort of guess this goes alpha, beta, gamma, delta, epsilon. That goes triangle to triangle to triangle to triangle. And then next comes zeta, which is over here, and then eta and theta. So, it looked like, to me like a Hamiltonian path. So it's kind of neat that whoever in antiquity put it on these letters was also going triangle to triangle and enjoying this idea of exactly the thing that Hamilton decided in the 19th century was an interesting thing to do with icosahedrons. Okay, so I thought I'll pursue it a little bit, and I tried to read up about it. I found a few articles by archaeologists about these things. They don't know. Nobody knows what these were used for. Maybe dice, because there are some that have a similar design to also a cube, which we know for rolling dice, and and a few dodecahedron have been found, but not with letters inscribed. And so anyway, I started looking more into it just to see how many of these. I can't see the back of this, so I don't know if it's really a Hamiltonian path or not. I just have no contradiction from the front of it. So half of it is missing. So I was making the trip to England, and two of the collections that had that I knew had these icosahedron were in London, and so I wrote to, and one was in the in a museum in London at the University of London. It's called the Petrie Museum. Let's see, I'll zoom out on this one. So, well, how do you go? Well, zoom in. Doesn't want to zoom much. Okay. Well, yeah, you can't. How do I? Fred, do I have to do something special to get it to zoom way back, or is there any other? Most of my pictures are not too large, but this one seems to be too. I would like to go way out if you can, but maybe you can. It doesn't seem to be movement. So this is a icosahedron, and next to it is a coin. This is a I don't know, 5p. I don't know. And this one, well, the light is so bright you can't really see the lettering on it. It's painted on, not engraved on. Here's another one that we found at the Petrie Museum. Yeah.
You can see on the other monitor with more color.
Oh, I see. I see. That's interesting. Okay, good point. So, and they let me, it's not open to the public except on rare occasions. But if I came on a certain day and said the password and so on, I was allowed into the room, and I got to put on special gloves and so on, so I could touch the stuff and see what these icosahedra were that had been made 1,800 years ago. And this was actually. It was the thrill of having something that old wasn't anywhere near with the thrill of just going from triangle to triangle, and actually it was fun to go through the alphabet and see the way. So I mean, there's some kind of a natural appeal to the idea of a Hamiltonian path. So I had a feeling of connection with these guys. Then 3 blocks away from the Petrie Museum is the British Museum, and I also got permission to go into their Egyptian Antiquities department, and they have 3 examples of the things. So I have one here that you can see the size of it, and another one. And another one. Okay, so and and this one was the biggest one, and so I took a lot of pictures of this one. And then they also had another one that was not a Hamiltonian path. In other words, you find these, and the majority of them seem to have this Hamiltonian property, but not all. And here's an example showing that this comes from the Institut Français of Cairo in 1930, and shows a lot of other examples from museums like the Louvre and in Germany and especially in Cairo of similar things. Okay, now so what I did was in my book let's see, I got to keep my papers from getting mixed up. So in Art of Computer Programming, I plan to have this image, which shows that large one from the British Museum from all 12 vertices in the middle. So you can so you can see that it is indeed has a Hamiltonian property, alpha, beta, gamma, delta, and so on. And from this image, I made a special design for today. Can you see this? Okay, this is my new font. I only have the letters, but you'll notice that at this time the Greek letter for sigma was like a Cyrillic S, not the way we write a sigma nowadays. Okay. So any questions on this? So then I put an exercise. You know, Art of Computer Programming has exercises. So I put an exercise in my book. Let's look at exercise 9. And keep this. I gotta keep. Whoops. Where's exercise 9? Okay, I'm sorry. I got to keep my pages from getting mixed up. I've got to discipline myself. This is my first run through of a talk I'm going to give next week at Stanford too. So let's see if I get it right next week. Okay, so exercise 9. Put up here. Okay, each letter in a Greco-Roman icosahedron can be placed 3 ways within its triangular face, depending on the choice of the bottom edge, except that delta and omicron are symmetric. So from this standpoint, the fact that pi and upsilon share the same bottom edge in the text example from the British Museum, the bottom of the pi is the same as the bottom of the y, of the upsilon is a little bit non-aesthetic. So anyway, I say now let's make a new icosahedron, a 21st century icosahedron, and so we're going to use the Roman letters, A, B, C, D, the first 20 Roman letters, and then we're going to do it systematically so that the bottom edge of the next one is always either going up to the right or up to the left of the current letter, and then we also want it to be a complete tour with T followed by A again. All right, so is there a way to do that? And so the answer to exercise 9, if I'm pointing to, but if I point to the board, then the people in the back don't see it. So I'm going to try to point on here. Yeah, but no, but it's a shame because I always wanted to use one of these. Okay, so here's an answer. It's essentially unique. And Hamilton knew this, that his original problem had essentially only one, up to isomorphism, had only one Hamiltonian path that comes back and is a Hamiltonian cycle. Now, whoa. So. And then I said it would be nice to own a 3D printed object like this. Now this is in notes that as I say there was no clickable index to these notes. However, in July, I got an amazing thing in the mail, which I have here somewhere on the table, and I'll show you that. Okay, it's not in this file, it's not here. Aha, okay, I'm getting closer, Okay, so, all right. Oh boy, okay, so all the clues are in front of me here. Okay, so essentially, the mail brought a package that came from Poland, and it's on one of these sheets here. So we'll see where it is. Aha, okay, all set. Okay. Okay, a letter from Poland comes from Krakow, and inside was a icosahedron. It said, "We make dreams come true, Science Center." And so then I looked them up. There's a startup company that's just started selling 3D printers, and I show you the what was in the box. So Cinterit's their new product, which just came out, and here's the. It's in black, so you can't see it too well. So I looked at it, and sure enough, here's A, and I go upper right, B, upper left, C, upper left, D, upper left, E, upper right, F. Yeah, lots of fun. Okay, so it's sort of the most incredible gift I ever got, and I didn't know who to thank for it, but I did have an address for them, so I sent them a check for $2.56. Okay. So, and I said, wonderful surprise. Thank you for one of the best gifts I've ever received. When I wrote, "It would be nice to own a 3D printed object like this," I clearly made a gross understatement. So the enclosed check is for correcting my manuscript. And in fact, so when you see when I make the next change to this section, it's going to say I received this. Oh, yeah, here it is actually, the new draft of the section. The author cherishes a 3D printed object like this, received as a surprise gift. So okay, all right, that's the story about icosahedron. Now that's only one story out of several, and I've taken 25 minutes, so I've got to. I'm going to keep you overtime because I don't want you to miss the other parts of the story. Okay, so now, there are three parts to the story. First part is Greco-Roman. Second part is Arab and Persia. The third part is India, and so we're going to go on to the second part now. So, okay, the second part is something. These British Museum stuff I did last year. 2015, but this year I learned about I had known for some time that there was this Arabic manuscript that had the earliest known examples of a knight's tour. Now I don't know. I figure this is a pretty geeky audience, so everybody here is going to know what a knight's tour. But in case you don't know, there's the game of chess. There's a piece called a knight that has a really interesting move, and chess has an 8x8 board, and there's a way for the knight to go from through all of those 64 squares, hitting each square exactly once, and that's called a knight's tour. And that's an example of a Hamiltonian path on another kind of a thing, not an icosahedron. And this problem doesn't go back as far as 200 AD, as far as I know. I mean, chess wasn't invented until about 600. But the earliest knight's tours come from the 9th century, which are the 800s, and in fact the first two Knights tours that are known come from about, I don't know, 840 or something like this. Although the date, when you go back this far, all dates are a bit hypothetical, but it's known that in the 9th century there was the world chess champion. Or I can back up a little bit. It wasn't chess was originally invented with different rules than we have today, but the knight move was the same. And it was called chaturanga or shatranj, depending on which country you're in. Shatranj was getting popular about 700s, 800, and in 842 there was the world champion, a guy named Arumi, and he published a book about Shatranj, saying how this is the way to be the champion. And now all complete copies of his book are lost as far as anybody knows, but other people picked up parts of it and quoted from it, and so we have hints from it, and in particular, 300 years later, somebody wrote that and quoted rather extensively from Arumi's book, and said, here's a knight's tour that he had come up with, and presented a bunch of other interesting combinatorial puzzles, but the knight's tour was the most interesting of them. And furthermore, this same author, whose name was Abu Zakaria Yahya ibn Ibrahim al-Hakim, so we call him Hakim for short. He also gave another knight's tour, but only one manuscript of al-Hakim's treatise survives, and that was made 300 years after he lived. So this manuscript has a very checkered history, and it has never been translated into English. And as far as I knew at the beginning of this year, it existed only in Manchester, in the John Rylands Library in Manchester. So I wrote there, and I asked, I knew what I thought what page numbers I wanted, and they said, okay, we can photograph this. It'll only take you a month, and if you pay us $75, it's good. And so I did that, and I waited a month, and I got and it was completely different. It was my Egyptian friend who helped me with Arabic stuff looked at it, and it was some strange poem about religion or something. It had nothing to do with chess. So then we found out, oh yeah, over the years they've changed the number of this manuscript, and it's okay. So finally. I got to talk, but I'd already paid this money, and I showed them the references that I had to it, and so then it turned out, oh yeah, actually we've digitized this, but we haven't told anybody yet. So then I could just look at it online, and I finally found the page, and here's the page where it has those 2 nights tours on it. Okay, if I could zoom this way, I go out as far as I can. Yeah, okay. So this is well, actually, though, I'm sorry, it's this way. All right. I didn't do that on purpose, but okay. So like on the type line, it says something like, here's how you can kill off all squares, and then you've got these. Okay, so what is this? What does this mean? Now the interesting question is, okay, you have a nice tour, but how are you going to tell somebody else what a nice tour is if the reader hasn't ever heard the concept before, and to illustrate it? So here's what they did. I'll show you on another piece of paper where I've done some marking here. I'm going to turn it sideways now. So that you can see just what was on the left-hand side before. And so here it says this poem is the word means sort of it housed. This poem is housed according to the right path of the knight, and then it gives a poem. So here we have Arabic 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 verses of a poem, and 64 words in these verses. And so the first word, if you match it, that goes up here in the corner, okay? The second word goes here. The third word, you find it there, all right, with me? If you, now, I looked at this and magnified it and so on and matched the patterns, and the handwriting, I think, is pretty awful. But in fact, it's a one-to-one correspondence between these 64 words and these 64 words. And similarly, on the right-hand side, there's another tour, and this is the one this tour is credited to somebody named Ibn Mani. And Ibn Mani doesn't appear in any other sources. Nobody knows who Ibn Mani is. But this is the one that I think is absolutely first in the world Knights tour, and I'll explain why in a minute. So now this word here is in that corner, and the second word, and so on. So this goes on 64 steps, and I actually on Tuesday night I matched them all and verified that in fact this is indeed the tour. And the tour, if you look at it in my book, it just shows as a diagram. The Ibn Mani's tour it starts in the corner and goes around, around and around in the edges, and sort of gets rid of the three columns on all sides, and then comes and ends up in the middle and winds up hitting everything. The other tour is by Al-Adli, I call him Marumi, the same guy, and this one is a closed tour. Now, we got a date for Al-Adli, 842. There's no date given for Mani's tour, but it's since it's not closed, and since it's much simpler, it's quite natural to think that this was probably found before this one was found. And so under that basis, then we can say there's some probability that this is the oldest known Hamiltonian path that's a Knight's of any kind, really, because the ones that are on these icosahedron that might, it's probable that they knew that they were going triangle to triangle, but maybe not. But this is definitely a Hamiltonian path, and so that's the way. It all comes from this page of this document, and matching those the poem to the square. Now the same document though continues to the next page and gives another notation for the first tour, for the closed tour. So the closed tour on the next page of the document, they show the closed tour in this form, and here they're writing. My friend could read some of the Arabic. This says, well, it's I put it here. This says first. This says second. This says third. This says fourth. Fifth, sixth, seventh, and then when you get ninth and so on, here's the Arabic number 30, and 40 is here. But then these other numerals my friend had never seen before. He thought it was some old Persian style numerals there. But anyway, this is then another way to describe that tour. Instead of taking a poem and redrawing it in there, you just say, okay, here's 1, 2, 3, 4. Follow it this way. Okay. So this was a pioneering way to also for notation to describe that tour. Now so in our notation, then we would have said 1, 2, 3, 4 according to this pattern. The way I showed you before, where we had a tour described with by actually drawing a path like that, that wasn't invented until 1766 in Italy, and I found that in the Cleveland Public Library. So okay, now there we are then with notation and Arabic tours. So these two pages, which are actually, one is the obverse of the other, are the only manuscript that that records these early tours. But they certainly are absolute tours, and there's very good sort of provenness that this isn't a fake. Okay, so here we've got 1,200 years ago, people studying Hamiltonian patterns, and it turned out that this was actually the first, because in India they also did Knight's tours, but only on a half of a board. So they were doing 4 by 8 instead of 8 by 8. And they beat they beat the Persians by 30 years or something. So there's in India we have a 4 by 8 Knight's tour that's fairly well dated now as 815 AD. And then another one in 830. So two different 4 by 8 tours. There's no closed tours on a 4 by 8 board. Now I got to now this is the most mind-boggling thing, is the way this happened in India. Well, more precisely in Kashmir. Now I've got some Indian things to show you, and in order to do that, I'm going to show you a little poem that I wrote. This is you'll understand afterwards why I'm doing it this way. Now if you take a look at the Knight's tour problem on a 4 by 8 board, it turns out that there are 62,176 of them. All right, and I chose one because it's the only one that allows a nice poem like quite as nice as this one. And so let me show you how this. Oh, I'm sorry, not this poem. I'll get to that poem later. This is my first poem, and I'll give you another poem in a minute. Okay, so let's see here. Try this. Okay, so here. Can people read this poem? Can you see this poem? It says, "Want a good time, lots of fun." Is that clear?
Can you zoom in a bit?
What?
Zoom in a bit?
Zoom in a bit. I'm zoomed into the max, and I shouldn't have magnified my font so much when I prepare this thing. Okay, but okay, can you guys read it at all? Okay, well, okay. So I first, instead of want, I had vant there instead, because it sounds like it's a foreign accent. But anyway, let me explain what there is about this poem. So I start here, and I say, want a good time. But now I also say the same poem, but I go another way. Want a good time. You see what I'm doing? I'm jumping by Knight's moves. So I have the same poem. Want a good time, lots of fun. Okay, well, lost, lot. That's poetic license. Okay, lots of fun. Okay, now not time so good. So now not time so good. Now not time. I hope I don't screw this up. Okay, now not time. So okay, foo. Okay, here we are. I guess I could have been drawing this. So want a good time, lots of fun. Here we go. Yeah, lots of fun. Okay, now not time. Now not time. So good. Now not time. Foo. Okay. Then so. Okay, so so. And here I have two choices. And so after so, then another so. But both of these choices lead to this guy. I don't know which one to choose, but anyway, I'm going to wind up here. So now fun is lost. So now fun is lots. Okay, and then time not now. Okay, well, time not now. Okay, good. Time not now, good. So time not now. No. So here it goes. So time not now, and this line should have gone from there to there. All right. So okay, applause. All right, now this is the method that was used by the Kashmiri poet Rudrata in 815, and he was this book that he wrote. The title of it was called Kavyalankara, and it means ornaments of poetry. It sort of means tricks with the most clever poetry ever devised. And Rajas would pay these poets to be the court jesters, and to provide intellectual stimulation, and so they would write poems in Sanskrit that had a very ingenious wordplay, and this became this became one of the highlights of the of intellectual thing, was to be able to show what great poems, what great clever poems you could write. Now, the modern Sanskrit scholars hardly treat this at all, because they say, well, there's no plot in this poem. It doesn't have much character development. There's not much, and so they don't see it as a real work of art. They think, if you change a few words, you get a much better, you get a much more profound psychological meaning of something like this. There was periods of time when this kind of thing is more or less appreciated. Now, I had previously known that there was a lot of great stuff in Sanskrit that anticipated things that happened elsewhere in the world. For example, binomial coefficients first sent me to Lilavati and then earlier Sanskrit documents, and then Fibonacci numbers came out way before Fibonacci's time in Sanskrit, and so I had already made some trips to libraries, and I learned how to match enough Sanskrit letters so that I could find the mathematical part. So then when I said it, okay, it's there's also Knight's Tours in Sanskrit. Wow, so I went to the library, and this was in Oxford, where they have a really good collection of Indian works, and so here's the page from Rudrata's book that has his little poem. Now his poem, it has only, has 32 syllables. That's just like my poem had 32 syllables. Want a good time. So his poem has 32 syllables, and it appears in this, and in Vedic poetry, the long tradition of writing poems that have 16 syllables in a line, and also the poems tended to be kind of cryptic. This is what he said. Now in my book I quote it and translate it into English. Where the heck did that page go? Okay. Yeah, here we go. Okay, so all right. So here I type that, but here so here's what it says. Se na li 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 na li li na li 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 na li le, na li na. Okay, so that's the poem. Only 4 different syllables in this whole out of these 32. There's only 4 distinct syllables. Well, the reason was that he only knew what I think he only knew one night's tour. It was this one. And so if he has to do that, he has to compose a poem that looks like this, where he's got, he has to compose a poem where he has a pattern, where his poem goes 1, 2, 3, 4, 5, but also at the same time, the same poem is also 1, 30, 9, 20, 3, and so on. So as you read this poem, and you read 1, 2, 3, 4, 5, you also read, that's the same as reading it this way. So in other words, in order to have a poem that does this, you have to have 1 equals 30, and then you have to have 1 equals 1. That's easy enough. 30 equals 2, 9 equals 3, 20 equals 4, 3 equals 5, and so you know this 9 equals 3 equals 5, and so on. So you keep getting equalities that are forcing you to cut down on the number of syllables, and you end up in this case with only 4 syllables. Now, of these 62,000 tours, there were 1,900 of them where he would have wound up with only 1 syllable, but fortunately he didn't know any of those. But the one he knew was one that left him with 4 syllables left. And so, but he did actually come up with something that makes sense. That's the thing about Sanskrit, that this wordplay makes sense. So I found a commentator that says, okay, this li na stuff. There are lots of words in Sanskrit that you can make out of li. There's some tricks like this in English too. I praise the army whose leader is mighty in play, which is devoted. I, who am not acquainted with untruth, whose men are mounted in cats and keep together in various vows, who does not perpetuate meaningless deeds and so on. This makes sense. This lili stuff actually makes sense, and just like my Vanda good time makes some sense. But the poem that I showed you in English it's the only night's tour that allows you 12 different syllables after you've done all the equivalences. So it was easier for me to do it. Now the strange thing is that there are actually 2 nights tours that match his pattern of lilis and na-nas, and nobody has ever pointed that out before. So we really don't know. I mean, all kinds of people say this was the first 4x8 nights tour, but no, there's another one that's equally likely, because there's absolutely no reason why because his notation was ambiguous. Now, Ratnakara was the next generation. He knew Rudrata, and he was inspired by that. So he makes his poems that are even more fancy with wordplay, and he writes a poem that has another way to describe Knight's tours, and he gives this Knight's tour by writing 2 poems, not just one. So Rudrata wrote 1 poem that you can read in 2 ways, and you get the same poem. Ratnakara writes 2 poems where each one is a poem, but when you read the one, you get the other poem. So here's my example of Ratnakara's thing. So. Okay, so 1, 2, 3, 4. Watch each word here, or take some left steps and move 8. Okay, so 1, 2, 3, 4. Here's 1, 2, 3, 4. Watch each word here. Watch each word here. Okay, you get the idea. This is. I'll be able to go through, or take some left steps and move 8. So here I have. A Knight's tour described by means of a pair of poems. All right, this you might think that this is really hard to do, but it only took about an hour, and I'm still wondering if this is the best poem. Maybe, if I change gives to something else, then I just have to change gives over here, and I get another 2 other poems. I just have to find the ones that somehow are most aesthetic. So here, so this is a wordplay from 1,200 years ago that are very early Knights Tour. Now you say these aren't closed Knights Tours because there are no closed Knights Tours on the 4x8, but this one starts in the corner and ends down here. So if I put another one right below it, I can jump over here and I get one that starts in the corner and it makes a Hamiltonian path. This one it starts at the bottom and ends right next to it at the bottom. So if I take this one, rotate it 180 degrees, and I attach those 2 guys together, I get a complete tour. So they were close to having a complete tour, but the guys in Persia with this Arabic manuscript I showed you, really showed a full board. Now, okay, so there's still some more to the story though. This example shows how the commentator of Rudrata explained the idea. Now you can imagine, what about the people in 815 looking at this? How are they going to know that's a Knight's Tour? It just says Li, 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 and so on. Well, they had one clue because he gave a Rook's tour in the previous verse. But really, these Vedas were tended to be very terse, and so Rudrata only wrote this, but all this other stuff on this page is a commentator by Nami Sadhu, who wrote 300 years later. And I'm not sure how the tradition got passed on for 300 years, but Nami Sadhu explains that this is a Knight's Tour and explains how you get it. And the way he did it was the following. At this part, I've got blue brackets about this thing. So here are 32 syllables, which are 32 different consonants now, if you put these, if you put these 32 consonants like this, and then you, whoops, I'm sorry, upside down. Excuse me. You put the consonants like this, and then you read them in alphabetic order. So all the Indian people would know this is, you go here, here, here. So you read them in alphabetic order. Then you get a Knight's Tour. And so on the top line there, he has those 32 consonants. This is a mnemonic, his mnemonic for Rudrata's Knight's Tour. And on the bottom is the Li, Li, Na, Na stuff that Rudrata actually wrote. So this chart now appears with Nami Sadhu's commentaries. This is how Nami Sadhu demonstrated what Rudrata was doing. This was. And this is Ratnakara's book. This was printed in 1890, and then here's the corresponding Sanskrit page, and here's his poems. Remember, he's the guy that had 2 poems. The first thing that, so I didn't have to learn Sanskrit. I just had to have a friend who knew some Sanskrit, but I also had to be able to find the page to show to the friend. But that wasn't too hard because you can look at these books and they have page numbers on them, and so you can first decode what's a 1, a 2, a 3, and a 4, and so on. So I found the verse that I wanted. Here's a 145. That's 145, and this is 146. And so then I knew that these 32 syllables are these 32 syllables, but rearranged as a Knight's Tour. And so here, so here's the example. And so this is the Sanskrit version of what I showed you in my English poem. And the Sanskrit, I numbered it 1, 2, 3, 4, 5, 6, 7, 8, and so here, so number 26 here, you find over here 26. Now, Ratnakara didn't actually use 32 different syllables. He only used 24 different syllables. He could have, like I did. I used 32, but anyway, it was still plenty unambiguous. And then there's a little problem because two of these don't match. Out of the 32, he's got 30 matches, and these two are anomalous. So now it could be that he used poetic license somehow, or it could be that, and it's more probable that it was just badly copied, because the guy's copying his stuff, he has no clue that it's supposed to be a Knight's Tour, and so you can easily make a copying error. And very few manuscripts survive, after 1,200 years go by. Okay, so now then there's another Sanskrit document. This one is from the 11th century, about 1050, by King Bhoja. It's called the Sarasvati, this one I found is online. I can find it from Oxford. Had digitized this manuscript. It's one of three examples of this particular poem from the 11th century. And this one has the nicest picture on the cover. But in this one, they used Ratnakara's method, namely giving two poems with 32 syllables each. But they used Rudrada's tour. So instead, so this tour that Rudrada knew, there must be something easy about this tour, because this thing written 200 years later uses exactly the same tour, but using Ratnakara's method to describe it. And similarly, a very famous poem by Deshika in the 14th century, called Paduka Sahasra. This is a religious poem about the sandals of Lord Rama, and there's a cult of Deshika. They recite this poem every year and have pilgrimages and things like this. And it's a serious poem, but it also has the same kind of wordplay. It has two verses that make a nice tour, and it has lots of other fun stuff like that in it. And I also found a Tamil translation of this particular thing. So here's the two poems in Sanskrit that by Deshika that differ by a Knight's Tour from each other. Okay. Yes, again, there are three other examples of the same Knight's Tour, different poems that correspond then. And I don't know if it's worth mentioning, but this. Oh, I'm sorry. One more thing, and I'm done with the Sanskrit business, and that is another guy. I'm sorry. Take it back. Somashvara uses the same Knight's Tour, but a different method of describing it. And so he invented yet another way to do it, and I got that. And so this is actually much more logical. It's more like modern chess notation. And so where do I have that? Okay. So what he does is he has an 8x8 matrix, and so he said, okay, I got 8 consonants and 8 vowels, and I can make an 8x8 matrix again. So I'll do this in English. So I have ba, be, be, bo, boo, ba, bai, bow. Da, de, di, do, do, da, di, I, da, and so on. So I got 64 nonsense syllables in here. Okay, so if I have 64 nonsense syllables and I want to describe a Knight's Tour, I just read them off in the order of the Knight's Tour, and I get sa, ni, su, nai, lao, fi, ba, do, fo, bu, di, ba, fe, la, ni, so. Actually, you can memorize this. If you learn it, so somebody wants, so it's nonsense, but nonsense things like this are pretty easy to learn, and so you can impress your friends with your Knight's Tour after memorizing this. And so this was Somashvara's way to do it. Of course, he didn't use the same consonants, the same vowels that I did. He used Sanskrit consonants and vowels, but there they are. It's, you know, pa, si, pu, si, tai, ni, and here is sa, ka, ta, na, da, ta, ta, and so on. So he gives the matrix here, and then he gives explanation following it, and actually inserts numbers in his document to underscore the point that corresponds to reading a certain order. And this is actually a kind of an authentic document, you know, well-edited document for this particular poem, and it has a long A here. Now, in Wikipedia article about this guy, they don't have a long A, but I don't know, you know, but I'm not good enough at how to input Sanskrit to the Wikipedia to correct this mistake. But I think probably next year Wikipedia will have it spelled the same way as this guy. All right. Well, anyway, this is so as I say, this is a story that remains to be told by experts. And I'm an amateur, but I'm gathering these facts, and here I find that there are all these extremely clever people living, you know, more than 1,000 years ago, and then you know, systematically every century there is also other examples. So this spirit was kept on. So I really think the Hamiltonian path problem deserves to be called the classic granddaddy of combinatorial, or let's say graph theory problems anyway. And it's something that arose in different cultures around the world and has a long, sustained history of very clever ideas that went into it. Okay, thanks a lot. Okay.
Maybe we take 2 questions only, and then we'll focus on the panel after the reception. So maybe 2 questions.
Okay, I see in the middle.
Yes, please come. We'll give you a microphone.
But don't ask me how to find one of these pages on the table here.
I think he found a misprint.
Oh, okay.
Sorry, what am I supposed to do? Just ask the question? Yeah. So are...
It's important, we're recording.
Oh, okay. Sorry, thank you. Yeah, so I'm curious about like the poetic and literary part of that at the end. So first, are you familiar with like the Oulipian tradition of writing using Knight's Tours and George Perec's use of it to structure life, a user's manual?
Yes.
And like, what do you...
Yes, let me tell you about Georges Perec. Yeah, life. Okay, so if you look at my... okay, I have a web page called "So You're Retired. What books are you interested in?" You know, and I say Life a User's Manual is my idea of the best novel of the 20th century. Okay, so there's a group in France that called Oulipo. This workshop of potential literature is the translation. And they were founded by several mathematicians, but also by Marcel Duchamp and you know, but a bunch of people. Raymond Queneau was one of the main people, but Claude Berge was a very active member of Oulipo, and also Pierre. Goodness, he's head of a big OR group in Paris. I just call him Pierre. So he published about planarity. So anyway, Lyonnais, several other mathematicians, as well as some Harry Matthews from America and Italo Calvino from Italy, and they've been meeting monthly and keeping you know, and I had the honor of attending one of their meetings in it was in March of '99, I think, and presenting some of the wordplay that I had been doing. And I'm a huge fan of Georges Perec, who is the absolute best of the Oulipo, but Claude Berge has some, he wrote a novel that's big, that has some graph theory in order to solve the mystery and things, a little short story. And so I indeed a big fan of this idea of working to constraints. And so when I had composed this poem, Pierre Rosenstiel was the first person I told about it, and he he wrote back immediately and said, yeah, Oulipo applauds this, and then he had me give a talk about it in Paris later on. And he said that the French hadn't seen this particular game being played before. I mean, thanks for that question, because I got to advertise all this other stuff.
Another question? Please.
Any results from China?
So I haven't heard of any Hamiltonian paths in ancient China yet. Good question, Tom. Yeah.
All right, so we will continue with questions after the reception. So we invite you in the reception area. We are going to toast for the 50 years anniversary of a seminal discussion between Professor Knuth and Professor Peter Wegner from our department. Please. And we will continue like in 15 minutes back with the panel asking tough questions for Professor Knuth. Okay. All right, so let's get started. So at Brown, we would like the question and answer sessions after a lecture, especially after such a lecture, not to be a few things at the end of the lecture and move on, but to give first-class status to questions and tough questions. And we selected 4 brave students that most of them are intimidated, but some of them are brave and said, I'm going to ask a question, Professor Knuth. So they will ask a round of questions, and then the audience continues. They will just get started. Before we get started, maybe the graduate students can introduce themselves. Please.
My name is Amy Becker. I'm a third-year PhD student here, and I work with Phil Klein on approximation algorithms.
Hi, I'm Cyrus Cousins. I'm a second-year PhD student, and I work with Eli Upfall on probabilistic algorithms.
I'm Colin McSwiggan. I'm a second-year graduate student in applied math, and I'm interested in topics across both theory of computation and mathematical physics and their intersection.
Hi, I am Lily George. I am a third-year undergrad studying computer science and literary arts, and I work with Professor Huang on user interfaces.
All right, so before the students takes over with a round of questions, I would like to ask Professor Knuth a question about the collaboration with Professor Peter Wegner. Can you tell us a little bit what you remember from those 50 years ago? I would like the day of the week when you guys talked, and things like this, but also the exciting part of it, please.
So, John, it's almost exactly 50 years, but the actual date was February of 1967. So next February will be the 50th anniversary of this idea that became known as attribute grammar. But in February I was asked to be an ACM lecturer, which at that time meant that they would schedule me for 3 weeks of lectures, 15 lectures in 3 weeks. And at the end of the first week, I was in Cornell, and it was Friday, and so then I stayed the weekend with Peter and Judith, so that then on Sunday night I could leave for my next lecture wherever that was. And the reason that I know that it was a weekend was because on Saturday, Peter and I went to his temple, and on Sunday he came to the church in Ithaca where we were. So we didn't only discuss computer science, but we discussed life and all kind of other things, and including kids, which we had young examples of. So, but the big question in computer science, what were the hot topics in those days, and it was how the heck do you describe the meaning of computer programs in a formal way? We were writing programs and we thought we knew what they meant, but we didn't have a way to really say exactly what we meant. There had been a conference where people proposed all kind of methods, and the conclusion at the end of the conference was, well, I can actually quote what the organizer said. If I can find it here. There was a big conference in Italy, yeah. So he said, wait a minute. Okay. Okay, so Fraser Duncan, who was a professor from Newcastle, said, we have not actually got all or perhaps any of the answers, but we have a lot of ideas of where to look and where not to look. That was the conclusion at the end of the conference, and also somebody said, I don't fully know myself how to describe the semantics of a language. I dare say nobody does, or we wouldn't be here. So it was up in the air how to do this, but the existing proposals were all about as hard as writing a compiler. So if you could write a compiler for a language, then somehow you could say, okay, that describes what the language means. Well, that was not very satisfactory. You want somehow to match the meaning of your programs with something that human beings can understand in a way humans understand it, not the way computers do. So anyway, Peter and I were talking about this, and he says to me, well, what do you think is a good idea? And I said, well, I kind of like some of the things that I'd seen recently that were based on saying you get the meaning of a whole thing by knowing the meaning of its parts. So, for example, if you know what alpha is and you know what beta means, then you know that alpha plus beta, with a plus sign in between, means the sum of alpha and beta. So we can define meaning in terms of, if we know meanings of parts of things, we can then define a meaning of the other thing. But this only went one way. It went bottom up. It went from the meaning of a small thing to a meaning of a larger thing. But then we had other things in programming languages where we had a statement that says X is replaced by Y, and we don't know what X is except that if we look up above to see where X was declared to be a real variable or integer variable or something like this. So some of the meaning was coming from the top down, and so it looked like it looked impossible because we have circular reasoning, and so I have a slide here that we might be can you show it on the visualizer? And this is a can you see this? Insanity is hereditary. You get it from your kids. So there's something about going. Usually when you talk about attributes, there's a one-way direction where things go. So there have been some very good proposals for going bottom up. In fact, I was editor of ACM Journal for the programming language section. I had just seen a nice paper by let's see, the co-author of Hartmanis. Okay, so there was where's the paper here? Okay, yeah, there was. Okay, I think I found it here. Yeah, Lewis and Stern, Phil Lewis and and Dick Stearns had just submitted a paper that would, but again, it was a very nice way to go bottom up. But so Peter said, well, but why don't you also go top down at the same time? And this is where we started to, and I said, no, you can't do that. And Peter said, well, why not? And so, because you can define this attribute top down, another one bottom up. And so if we have a tree there, we can walk around the tree, and some of the attributes get defined in one direction, some get defined the other way. And then as I was arguing with him, I started realizing that I had started shouting because I was beginning to realize that his point was right and mine was wrong. So this was a beautiful day in the winter of 1967, and without that conversation, a lot of interesting work would never have been done. So that's why we're happy to celebrate that now. I got one more historical thing while we have the type right here. I came to Brown in 1979 when, I'm sorry, in 88, when this building was dedicated. And I believe I spoke in this very room. And I was wearing this exact same outfit, which I only wear at this time of year. And I spoke on the 4-volume problem. That was the title of my talk. And so I found this slide that I had used on that day, just to tie in with the history that was 28 years ago. So, and this was the beginning of what became a Stanford graph base, which is a set of data that can be used to compare algorithms with each other in an interesting way. Okay, that's history.
And this morning you played organ in Sales Hall, and that was the same hall where?
Where I got the doctorate at that occasion.
The Brown honorary doctorate degree. So it's a lot of continuation. So now maybe the graduate students and the undergraduate student might want to ask a question.
He puts you on the spot first.
Here. So thank you so much for coming. I guess my question is sort of half-asked by Peter Wegner earlier when he talked about your Project 316 when you did the random sampling of the Bible. I was really interested in that, and I guess my question was what were some of your takeaways from that, in addition to what do you think is the limit to which computer science can help you understand matters of the faith? And also, that project was undertaken in the 90s, and there have been hopefully more developments since then in computer science. And I guess, was there anything that has struck you as something interesting that you might like to explore, even if you haven't personally done it?
So
that was a lot.
The idea was it's based on random sampling, which of course the randomization, the more every day goes by, we learn another use for randomization. And so at the time I did this work, which was the late, well, I started in the 70s. I've been using randomization to understand complicated things for a while. For example, a student turns in a term paper, and I have to grade the term paper. There's a big, 50-page paper. I can't read that all. I've got 60 papers to grade. Okay, so how many? So I took a random sample. I would turn to a random page of the paper, and I would read that carefully, and then I based a grade on that. The student wouldn't know which page I was going to choose, but this was a perfectly good way to do it, and the Gallup poll had come out a lot earlier, of course, with the idea of random sampling was well known. So I've used it for a variety of things over the years. Some people thought I just graded at random. That wasn't completely true. But then I decided one time, well, the Bible is a complicated thing. So what if I look at a random part of the Bible? But the idea of the methodology is then that I shouldn't be. Nobody should tell me what verse of the Bible I should look at. but it should be something that sort of every verse is equally likely. And then I could go to the library, and with the Bible, you're lucky because thousands of books about the Bible have an index in the back saying, if you're interested in such a verse, it's mentioned on page 28 or 30, okay? So for example, John Calvin wrote 100 volumes about the Bible, and I would never open any of his books. But if I only had to see what did he say about these 50 verses, then I could read 50 pages of Calvin's writing, and I could get an idea of Calvin. So in other words, the random sampling was not so much of learning about the Bible, but learning the secondary literature of the Bible, understanding what other people have said about the Bible over the years. And so this was a good way just to get me jogged to understand a complicated subject a little more, to get some more insight in the maximum amount of insight per hour or something like this. And it turned out that what I found was that, you know, a lot of people had put interesting thoughts into this, and also I found some trivialities, as you can imagine. I mean, I was doing this random sampling, and I found people who were like bloggers who just like to write, but they didn't have much of ideas, but they had really wonderful vocabulary. So I tried to learn their vocabulary. But the random sampling helped very much for me to understand a complicated thing that a lot of people have written about, but it's much better than if somebody had say, okay, now read this part, and then and especially then I could understand literature. So I use it for. I use computer methods also in the Stanford Graph Base that I mentioned here. I took several novels and I just found the graph of who meets who in the novels, and I found as I'm reading the novel, and I have I have a little notebook, and I say, okay, now X is meeting Y here, and I write that in my notebook, and I'm just thinking about that that helps me appreciate the novel. I mean, I don't do this with trash novels, but you know, for Anna Karenina, I found that this enhanced my appreciation for Tolstoy by keeping this extra thing, and then I made a little graph about it, and I could. So I really believe that computer science it helps us. The technique of computer science helps us understand things that you might not think immediately identify with computing. Okay, thanks for your question.
Thank you.
So, as someone who has been working in a field for a while, you have had an opportunity that many of us have not had to, in the past, imagine ways that the present state of the field, our present world, would be now before it came to pass.
Yeah.
Those of us who are younger are inevitably, to some extent, blinded by the world that we're given. We take aspects of how the field is for granted. We believe that things are inevitable or necessary when really they're not. For the sake of widening our perspectives, I'm wondering if you could share either a hope that you had in the past for how computer science would be today that has not been realized, or a regret that you have about how the field has developed, or a moment in the history of computer science that if you could, you would go back in time and stop.
Well, okay, that's hard but it's a great question. I would rephrase it saying I lived an easier time where I didn't have all this blinders, but also there weren't that many of us doing it either. So you could be a big fish in a small pond in a way. If there's a huge number of people working on something, and everybody tells you that these are the only important questions, well, that's a completely different situation for where it was. So you know, the answer to that is not to believe what your peers tell you is important, and to decide what you really think is important, if you can. And so, how do you do that? And one, well, it's not a perfect answer, but one trick I have when I'm reading the work of somebody else. I don't just read it through, but before I turn the page, I try to guess what's on the next page. And the person will state a problem, and I say, oh, how would I solve that problem? Okay, or what is this problem interesting, or what's good about it? And I usually don't get the answer. But I spend a minute thinking about it before I turn the page, and that gets me ready for that next page. And also when they start doing it, I start putting it into my own language. Every author has its own, you know, you have your favorite way to describe something. So I draw a picture, so I write down a little glossary of this author's term versus my own way of understanding it, and then I turn the page and I try to see. So then, when the author has come up with a new idea, I'm ready to absorb that idea, and I can see, oh yeah, here's a new thing that I didn't know how to combine these two together. And on the other hand, when the author does something trivial, then I also say, oh, I don't want to go that way. So this way of not just of trying to, well, in the '60s, everybody said question authority. Say, you take the attitude, it's not fair that I was born now because, when everything is already prescribed for me. So I'll pretend that I get to make the rules. And in fact, those rules, there are a lot of rules that haven't been done right, and somebody's going to come up with them, and only if they have that attitude. Okay, now, but then this other thing about what went the wrong way, what went the right way. So I was never very good at predicting the future. When Niklaus Wirth was asked, he gave a talk at the Computer History Museum about 5 years ago. You know, what's going to be the future of computer science. So he took every current trend that he disagreed with, and he said, okay, this is going to be more of this. It's going to get worse. You're going to have to choose between 50 libraries for stuff, and every subroutine is going to have different order of parameters, and you won't be able to write your own code, but you just have to choose from a menu of options. Life is only going to be a matter of plugging into one subroutine of parameters from another subroutine and so on. And so that was his way of predicting the future. Well, I don't think he really believed it, but it was a clever way to answer this question that people like us get asked. But on the other hand, we're old fogies and we see things with an old-fashioned way. So the way we look at stuff might not be the right way. We're stuck in the way we developed our intuitions was when machines were slow and small, and that might not be at all relevant at all at the moment. So. And so there are things where we should be more sloppy, and other things where we feel modern generation is being more sloppy. They'll say, "Oh well, too bad." But the thing I'm most worried about now, and also your chair, is the short attention span that people have. I ask a lot of questions in my book that I don't think you can answer with a short attention span, and I think it's important to learn how to do things to do things that can't be done when there's loud music playing and so on. What do I regret the most, or would wish to stop, was the was the connection between computer science and Wall Street as being considered the main importance of computer science. People tend to rate a computer scientist by how many startups they have or something like this, rather than how much interesting work they did, or something that will advance civilization somehow. You know, I can see the fascination of trying to make money with Bitcoin by devising a highly parallel algorithm that does some computation and therefore brings money into my pocket. But that only moves money from some pocket to another. I don't see how it advances civilization, and it also consumes a lot of energy in the process. So if that trend continues, where more and more electricity every year is spent computing blockchains, then civilization is doomed. Okay, hi Svante, what are you doing here? Are you Svante? No, you look like Svante Linison. You're not. Oh, okay.
So I'm wondering, you talked a lot about Hamiltonian paths on the chessboard, and there are several different pieces, including trivially the knight, the rook, and the queen, that could make similar tours of the chessboard.
Yeah.
Now, I'm wondering about a related question, and I was told to ask a hard question.
Yeah.
So I don't expect an answer per se, but I'd like to know how you approach this.
How I approach what?
Don't worry.
The question.
Yes.
Okay, yeah.
So, suppose you and I are both allowed to select one piece and place it anywhere on the board, and
This is a
we're-
chessboard.
Yes,
8 by
anywhere
8.
on the chessboard.
Okay.
And we're following the standard chess rules, and we want to take our pieces and together cover each square of the board exactly once, and then one piece captures the other. So, does this problem setting make sense?
Not quite. You're saying that you have a piece, I have a piece, and then we each do 32 moves, and then you capture me?
Yes.
Okay.
So,
And you're going to choose that piece once,
yes, we choose the piece at the beginning.
and then I get to choose my piece?
Mhm. So for which
You move
combinations?
first? Oh, okay. Oh, I see.
It's symmetric.
Oh, I see. Oh, all right. I see. When is this possible?
Yes.
Oh, and we move alternately?
Mm-hmm.
So, you know, it's true that that a guy named Thomas Rainer Dawson invented some puzzles where you alternately move a bishop and a knight or things like this in the 40s. But what and so is there? It's a. You just want to know the sets of things for which this is possible. Okay. Well, and the way I would attack it. Okay. So the one thing I learned that's not too commonly known is that Hamiltonian paths are not difficult to find. I mean, I told you that there are 62,000 knights tours on a 4x8. And Rudolph only knew one of them, presumably because it's passed down from generation to generation through some 100 years. But when you get to the 8x8 board, the number of tours is, it was finally enumerated in the 90s by goodness, who was he unfortunately died of cancer. He wrote the wonderful book about BDDs. But he and another guy had a paper where they had used all kind of computers and they put together the answers and they got the number of the knights tours on 8x8 board. And it was some huge number of 17, 18 digits. And however, I knew that the number had to be congruent to 2 mod 8 because of mathematical theory because I knew the number of symmetrical tours, which was much more easy to enumerate. In other words, you have to do 32 moves. The moves are always opposite. And so based on the number of 32, I knew that their number had to be wrong. And then so this, it was it was in this journal, what was it? Herb Wolf's journal on combinatorics, the first online journal, and so they had to retract it, and then the guys in Australia verified a correct result. So anyway, it's a huge number, and almost every problem that I look at, there are many Hamiltonian paths. So when you ask this question of which pairs of pieces is true, I would say, essentially, I would be surprised if there's any pair of pieces that it's not true for. Well, okay, pawns can only move one way. Maybe you have to promote them or something. Not only are these paths numerous, okay, it's not easy to find one unless you have a system. But if you have a system, then there are very fast algorithms to almost always find a good Hamiltonian path. So people who the French guys, he tried 8,000 problems. You know, this NP-hard problem, is there a Hamiltonian path? But he tried 8,000 problems that arose in practice, and they were all sort of solvable instantly. So Hamiltonian paths are almost ubiquitous. You know, after looking at that problem, I would say, maybe I have to put some more constraints on here. Otherwise, it's not a very great problem. And okay. So then we say, okay, now we want a Hamiltonian path in which for example, we have to wind around the board clockwise or something like this. You know, we disallow a lot of the legal moves of chess.
I think if we wanted a harder problem, what would interest me is how many such paths are there? For
How many
different
paths there are, and that so for that. That's P sharp. I mean, that's very hard to compute.
Yes,
okay.
I wouldn't expect an answer.
I don't know. I don't know if anybody has computed the number of Knight's paths, Knight's tours, the closed tours. But if you just go 64 moves, but you don't come back to the starting point, I think we're about ready to computers are enough computer speed now to do that, but I don't know if anybody's done it. Maybe I'm wrong on this, but I haven't heard about it.
Thank you.
Mm-hmm.
As someone who studies various theoretically classical problems in covering and packing problems on graphs, I was really excited to see that you were giving a talk about Hamiltonian paths and cycles. I don't study that problem in particular. I feel like in some ways the field as a whole has sort of moved away from some of these more classically theoretical problems in favor of things that are more applied or practical. So my question is, you just gave a talk about kind of a very rich history of these types of problems, and I'm wondering if you could speak to the relevance of these types of problems moving forward into the future, or even presently, and kind of this distinction that's made between, much like you presented, these problems as being more puzzles or games or art, and how that continues to hold relevance in the field.
Yeah, right. I love puzzles primarily because I can explain them in a short space, but to solve them, I can use techniques that I know are going to be the same techniques as I would use for some practical problem that would take me several pages to explain. But I face this dilemma. I'm trying to write a book that people will learn from, and if I base all of my examples on puzzles, there will be somebody who says, well, but this is only for puzzles, and I only deal with the real world. On the other hand, if I start talking about more complicated constraints, where you have to know something about biology, or you have to know something about quantum mechanics or something in order to understand the application, then the readers say, "But, you know, but I've never been good at biology," or something like that. You know, I ripped out 10 beautiful pages of volume 4 that was based on baseball. I mean, I love baseball, and I know that I know a lot of people who are you know, go nuts about algorithms that you can do with baseball, but when I looked at it and I thought, and I started to think, you know, how hard it is to explain these rules, and what if I had been reading a book that was all about cricket, you know, I wouldn't have cared about it at all. And so I left out baseball, I left out bowling, although these were some really interesting things that I didn't, from those problems, I didn't have any algorithms where I could learn anything more. But with the puzzles, I don't not only choose a random puzzle, but I choose a puzzle for which the method that I'm using actually generalizes to lots of problems that I know. So now, of course, the Hamiltonian path is a very special case of the traveling sales rep problem, where you had weights to the thing. So you have, not only do you want to hit every square, but you want to, but you have some cost of getting from one square to another, and you want to minimize the total cost. So that's an extremely practical problem of all kinds of things that you want to do in robots. You want to wire a whole bunch of things together. So you want to minimize the motion of an arm, but it has to hit all the spots. So these kind of things arise in industry all the time, and the algorithms that we use then to study Hamiltonian paths, the same kind of data structures apply, and so on. And the same kind of techniques for proving bounds on them are good. So that's why I've been you know, tending to use examples based on puzzle. There are the other kind of people that say, but now you're spoiling puzzles, because it's like taking dynamite to a trout stream, and you're just killing all the fish, you know, because you got these powerful tools, instead of spoiling a good recreation with things that you should be able to figure out in your head. And now you're using computers, and you can't win them all. But I personally love the idea that the ideas that we recognize now as computational ideas are part of world cultures going way back, and that even though they didn't have computers then, they had some of the same cleverness that we use to do our programming, and I can sort of feel that. You know, I read some Sanskrit document where, in translation, where I felt that the guy was talking to me from the 13th century. You know, he was asking the kind of questions that I'd ask myself when I was learning to program, and so I get a thrill out of that.
Wonderful. We should open to the floor, so other questions can be asked. There is a microphone, that please use it.
Thank you. Hi, Professor Knuth. So I have a question that is kind of inspired by an essay I read by Professor Richard Hamming, who was a mathematician known for Hamming code and Hamming distance. Yeah. So he has this famous talk called "You and Your Research," and he talks about working on, you know, the most important problems in your field. So as someone who has been in computer science field from the very beginning, and you have been writing about it in your Art of Computer Programming series of books, you have seen the discipline grow and become a really large body of knowledge. So what do you think are the biggest problems in the discipline in two categories, as a scientific discipline and as an engineering discipline?
Oh, I was afraid somebody would ask a question like that. I mean, okay, the generic type of question that that I least am happy about. I'm not going to duck it, but I want to tell you first so that I don't get any more. Is what is the most important thing in X, or what is your favorite of X, or something like this? And this is like asking a parent, which is your favorite child, or something. And it just you like each one for its own reason, but you can't compare apples to oranges and say something is better than others. So there's just every day I see something else that I think would be cool to work on. I mean, and I don't know that it's really a good idea to rank one over another. In non-computer science perspective, for example. Suppose that we're talking medicine, and so people were saying, okay, we're only going to work on cancer. Right? So there's lots of other diseases. So why should you ignore all those other diseases? In fact, why should you ignore dandruff? I mean, why shouldn't you spend, have a huge research lab that finds a cure for dandruff? It's not killing anybody, but it's, it quality of life type of thing. Why do certain things have to be considered the most important? There's no shortage of things that are calling out to be solved, and we're not in any crisis of think of some application of computers. The crisis is find people who know enough about computers to come up with good solutions to these things.
So as a follow-up, just wanted to compare basically, because I mean, we as a scientific discipline, or computer science as a field, is relatively new compared to mathematics or
what?
Computer science
Yeah.
is a new field as compared to mathematics or other engineering disciplines. So my question was more related to that. How do we make sure it matures in a...
So what did Hamming actually disagree? Did he actually say something was more important than something else?
No. He was just interested in asking people working on different fields, like
Okay.
what are the most important problems.
Yeah. But I mean, John Hammersley said he went around talking to his colleagues, saying what was the most important thing to teach in the schools, and his colleagues that were studying Icelandic poetry said, well, you needed a working knowledge of Urdic verse or something. I don't know what it was. Anyway, but everybody thinks that their own field is the most important, and I'm glad about that. Because I don't like to see things ignored. On the other hand, you're right. Computer science is much younger discipline than mathematics, and we tend to actually be much more. We've sort of been evolved to being able to come up with new problems every month, while the mathematicians are unhappy to work on problems that were posed 40 years ago. I mean, I've seen papers where the author starts out and he apologizes for working on a problem that could have been stated 5 years ago. I can't believe that this is a good strategy, because I think good computer science, just like good mathematics, has long half-life.
Any other question? Peter.
Yes, maybe you could say a little bit more about the relation between mathematics, physics, and computer science. To me, mathematics seems to be older, because certainly Pythagoras was primarily, I think, mathematical and not particularly either computational or physical. And then Newton developed physics in a way that beyond other people, and was highly praised for the physics, although he was also praised because mathematics was a form of expressing physics, I believe. Mm-hmm. And then computer science came along much later, and the question is it something new and different, or are they somehow all related to each other in some way?
Yeah, so it's hard to draw boundaries, but here's the way I look at it. So there are, there's a huge difference between mathematics and physics and mathematics and the other previous sciences, and that is that with mathematics we get to make up our own ground rules, and physicists don't. Physicists are given the universe, biologists, chemists, and so on, one of the tenets of physics is that you can't actually observe all of the universe. The observations are, there's an uncertainty principle there, so that the physicist knows that he'll go to his grave without ever knowing that anything he did was correct. And so I have to admire that. That's very, very courageous. And of course, I'm glad that people don't mind going through their lives this way without. But for me, I was really glad when I discovered. I started as a physics major, and I discovered that this is before computer science was on the scene. And so in mathematics, I could have some things where I actually knew the answer, but also I could choose to make up new axioms so anyway, there's the sciences where it's based on nature, and then there's mathematics which is based on reasoning. But not, that doesn't have to coordinate with anything else. And computer science is in that category. We get to make up our own ground rule. But on the other hand, there's so many different. I've known so many mathematicians who never thought about anything finite. I mean, the intersection between me and them was countable infinity. I never thought of anything uncountable. Well, I think of the real numbers once in a while, but they prime numbers and so on mean nothing to them. But they were dealing with mathematics that's pure reasoning, but about a completely different kind of things than a computer scientist tends to talk about, and then we have, as you know, even logicians used to distinguish only between solvable problems and unsolvable problems, not between problems that have high complexity and low complexity. So having some notion of computation by a finite device, it is rather different from most of mathematics, and I found that the main characteristic between typical computer science and typical mathematics from this point of view is that computer scientist works with heterogeneous models, and mathematicians work with more uniform models, where you have mathematicians will have one or two rules that explain everything, while computer scientist says, oh yeah, but here's case A, case B, case C, and here's how you distinguish between these cases. And so the people who tend to work in one area or the other are better or worse at at thinking about uniform rules. If there's something that where there's a uniform rule, I might not see it. I might find 5 rules that would boil down to the same thing. But for me, it's no big deal to think about 5 different rules. On the other hand, a mathematician will see right away that this is one rule. On the other hand, if there's a problem that needs 5 different rules, the mathematician will say, "Oh, this is hopeless," and the computer scientists will say, "Well, yeah, you should do it this way." So I see a difference in personality between these things, but there's difference in personality between topology and geometry, between geometry and algebra, between some kind of complexity theory and some kind of automata theory and so on. In computer science, the journal Theoretical Computer Science has 3 tracks, A, B, and C, usually A or B. One tends to be logic track, and one tends to be algorithm track or whatever. And I find that I can understand almost only half of them. So they're both called computer science. But I could argue if I was a person who liked arguing, I could argue that mathematics is a subset of computer science, and I could also argue that computer science is a subset of mathematics. And I find I sort of every 10 years I switch sides as to who I hope is winning.
Right. Trump, of course.
I wanted to ask kind of a follow-up to the question that was asked by the man in the front row here. You might not want to state a ranked list of priorities for computer science, but you must have very clear priorities for yourself because you're an incredibly prolific person, and you can only be that way if your time is organized in a very particular fashion. So I'm wondering, when you get up in the morning, how do you think about what it is that you're going to do before you go to sleep again?
Well, my wife is sitting there laughing. Okay. No. There's usually one thing that's bugging me that I have to know, but I don't know what muses that. It's something that it has to be done, and so if it's not Wednesday, if it's Wednesday, I know I have to do the laundry and stuff, But on other days of the week, I usually never have a question about what it is because there's something nagging at me. I wish I didn't have standards where I had to answer these questions because then I could get it out of my mind. But sometimes I just have to know the answer to something, and it might be stupid, but I can't tell myself. Finally, I convince myself, this is not going to lead anywhere, and then I say I'm never going to get the answer to this, but I know who I should tell. Like Richard Stanley was here. I don't know if Richard's still here, but I send him a lot of questions that Richard, yeah. So you get my wastebasket, right? So yeah, I mean, and vice versa, I get questions. But I guess in a way the thing that I learned early on was how to ask questions, which you obviously know how to do since you've asked 3 good ones already. But in general, but then I get real interested in them, and I have to learn how to put them down. But a lot of times things come magically, like Ramanujan said he was getting stuff from a goddess or something. I don't know, but I'll wake up like I wrote the beginning of this Hamiltonian Path section one morning when I said, I want to explain about these Indian tours. So I wrote up about what I knew about it, and that's why I have several other things that I started. And while Well, the iron is hot or something, I don't know. I don't have to go and say, what should I do today, or even setting priorities. It's not, and I've never been a strategic guy where I say, try to plot a strategy. I'm mostly just downhill, follow the flow of whatever is bugging me.
So it seems then as though you're saying that you're extremely lucky.
Yeah, well, I can tell you some other stories too, but no. I mean, you say I've been prolific, but you measure it how much per day, and it doesn't turn out to be much. I'm 78 years old, figure out, and I don't watch television. So.
Please, in the back.
So Einstein famously said, am I up yet? Einstein famously said that God does not play dice.
God does not play dice.
God does not play dice when it came to the quantum mechanics revolution.
Yeah.
But you use all kinds of probability theory and randomness and things and work that you've done. And I was wondering if you maybe had a more sophisticated understanding of like the relationship between, I mean, I guess the idea was that God had kind of a deterministic universe or something.
Yeah. Well, I don't claim to be a philosopher. I started to get the idea of what it would mean to be a deterministic universe by studying the game of life. I'll talk a little bit about that tomorrow, actually. But Conway's game. So we know that with a grid geometry and only two states, every computational process can be described. So if the universe is finite, one of the things you could model with the game of life is this session we're having today, and your question to me, and also all the multiverses that are similar to it. And that would all be some pattern in some game of life that exists. All right. So that's a deterministic universe. Well, I don't know anything about that. I'm never going to assert that God is going to do something or something not. In fact, I discussed this once with Michael Rabin, and we said, well, what, God could perfectly well throw dice if it was a good algorithm. I mean,
All right, maybe a couple more questions and then we'll go to dinner. Please.
So the last time you came to Brown, we had a history department, we had a mathematics department, but we also had a history of mathematics department.
And I visited David Pingree and I talked about Sanskrit mathematics with him.
So we don't have that anymore. It's about 10 years gone. And I can say that when I was an undergrad, the closest I got to history in computer science was learning that, Sun City had 5 bridges. So what do we lose by not learning things like the wonderful history behind Hamiltonian graphs? And do professors have any responsibility to teach that?
Okay, so let me say that this was the worst failing of mine as an advisor of PhD students. I wasn't able to instill in any one of my 28 PhD students the love of searching for historical source materials. To me, this is extremely important because I'm seeing how other people solve problems. I'm seeing how they did. I'm getting all kinds of case studies of successful breakthroughs. But by reading what people did in their own words, not rehashes of it, but looking at source material. So it's secondary here. This Arabic stuff. It was copied 300 years later and then copied again. But I'm still some of the Indian stuff I was telling about. We're pretty close to what the author wrote. And these authors were ahead of their time, but you can get some idea as to what they were thinking, and that helps you come up with better thoughts on the problem that's going to face you next week. And so why do people not see that. I don't understand, but I didn't succeed in getting any single one of my students to do that. And now there's so I gave a talk at Stanford 2 years ago called "Let's Not Dumb Down the History of Computer Science." And so it turned out that there was a paper. You can see this on the web, but there was a paper that started it by Martin Campbell Kelly, who is sort of the dean of historians of computer science, and his paper was called "The History of Computer Science," and he started out, and so he went through year by year, and he said what were the top 3 papers each year, and then he classified these papers into 5 categories. One was technical, and one was economic or something like this. And essentially, the first 5 years, they were almost all technical. The last 15 years, 0 technical. It's been a sea change. And he's saying, and this was a good thing. He's saying, I'm not going to teach my students to write papers about technical. I'm going to teach them to write about papers on how they got funding, you know, or whether they were discriminated against because they were a minority or something like this, but not ever talking about really an algorithm that they did or the breakthrough that they did. And you know, and Ed Feigenbaum told me on Tuesday he had been talking to Tom High, who has a new book about ENIAC, and High said, well, you know, he hopes he can get away with publishing a book that has some technical information in it about the ENIAC because he can't get this stuff published in papers, in history journals. Now the historians have a problem, not only that they're all on this bandwagon where you have to write history so that it's for the masses instead of for the scientists. But yeah, I mean, you could someone has to write for the scientists to tell them how to do the science of the next generation, or how, and the human story of how people rose up to face difficulties, and getting funding is a part of the story, but it's not the whole story. So you got to have a combination of breadth and depth, and they say no, throw out depth. You know, just do stuff that's, you know, because then they can guarantee that all the other historians are going to understand their papers, and the other historians are the only ones that control their tenure. And the fact is, there's not a single department of computer science in USA that pays for a historian of computer science. So where are they going to get a job? So I'm you know, trying to work at Stanford that we hire a full-time. Maybe Princeton has one. I don't know, but they did at one time. But you know that some computer scientists have to step up and say history is important. So that the historians can live, and if they, you know, they have to survive, and they have to write about something that their peers will understand. So if they write stuff that's too technical, then they're going to chastise by their because their colleagues don't want to admit that this is too hard for them. I mean, nobody wants to, you know, to say that they aren't able to handle technical stuff. But the fact is, you need a special kind of a mind in order to do technical stuff. So you need a crossbreed. You need somebody who does it. So no, historians of mathematics still haven't fallen victim of this. They're still carrying the torch, but they're fighting it.
Thank you.
I think we should end now. We have to go to dinner, but we'll continue tomorrow. So it will be a continuation. So let's thank the speaker and the panel.